Okay, in 10.2, we're going to be looking at something called the fundamental principle of counting. Anytime somebody puts the words fundamental principle inside of mathematics, it means it's really important. There's a fundamental principle of algebra. Whether you called it that or were told that or not when you were in algebra course, you've seen it before. When I teach calculus, there's a fundamental principle of calculus. Right? This is the fundamental principle of counting. But before we can actually talk about what that is, we need a little bit of notation that you may or may not have seen before. That notation is something called a factorial. Okay, so with many things in math, writing out generic formulas for something makes them look harder than they really are to work with. So simply write it down for the moment and we'll talk about how it works. What this is saying is that if you have counting number n, and you have an n with an exclamation point after it, we call that exclamation point a factorial. N factorial means we multiply n times the number 1 less than it, and the number 1 less than that, and the number 1 less than that, all the way down until we get to the number 1. That's the definition. And then we also will need it for some stuff we're doing later. 0, which is not a counting number, doesn't fit with this definition, so we need to define what 0 factorial means. 0 factorial, by definition, what we're defining it to be is the number 1. Okay? Okay, so generalizing things in math often makes things look more complicated than they are. I gave an example in my earlier class, and I think it's a pretty good one for what we're talking about here. My children are working with story problems right now in their Algebra 1 class. And my son in particular was struggling with this idea of relating these quantities that are unknown together. They're doing like systems of equations. So it says something like, Jack and Jill have, that's not a good example. I want different letters. How about Jack and Mark? Jack and Mark have $450 total. If Jack has $25 more than Mark, how much do Jack and Mark have each individually, right? And so they do things like where they say, kind of like what we did with all of our people a minute ago, they say Jack is J and Mark is M, right? That's how much money they have. And so when I ask my son, what does it mean for Jack to have $25 more than Mark? He's just like, I don't know, because I don't know how much either of them have, right? But if I say Jack has $100, or I did it wrong the way, Mark has $100 and Jack has $25 more, how much does Mark have, or Jack have, the other one? He can do it because there's numbers, right? Like when we put the numbers in, it makes it a lot clearer and we see what's supposed to happen. That's what's going on here as well. So we've got this formula given to us in these general terms, but putting the numbers in makes it clear up a lot quicker. So when I see 5 factorial and I apply that definition from the previous slide, what it's telling me that I'm going to do is multiply 5 times the number 1 less than 5. What's 1 less than 5? 4. And what's 1 less than 4? 3. And 1 less than that? 2. 1 more down, 1. And when I get to 1, I stop. That's all a factorial is. It's shorthand notation. We do this in math all the time, but you do it all the time as well. TBH, LOL. THX, right? You text it. We shorthand things all the time. This is just math shorthand. That's all it is, okay? So what is 5 times 4 times 3 times 2 times 1? And your calculator is going to be very helpful in these problems, 120. So if you have it with you, get it out. If you don't have it and you want to use your phone today, that's fine. Obviously, when you get to a test, you're not going to be able to do that. But grab something out. You're going to need some calculation tools for this section. Okay. Now, number 2. Number 2 has 8 factorial on top, and it has 4 factorial on bottom. And we're just going to list them out, just like I did with my 5. Okay? So we're going to write down 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, and on the bottom I have 4 times 3 times 2 times 1. Everybody good with that so far? Just writing them down. Okay. Let's just do the numerator for right now on your calculator. What is 8 down to 1 if you multiply them all? 40,000, say it again, Samuel.
320.
320. Okay. And what is 4 multiplied down to 1? 24. And if I divide these two things, what do I get?
1,680.
Fabulous. Did everybody's calculator or phone or whatever, did everybody's thing give them that? Look okay? Now, that's fine. But notice, when we had 5 factorial, it was 120. And when I had 8 factorial, I'm already at 40,000 something. These numbers get really big really quickly, don't they? And it doesn't take much further beyond for your calculator to not be able to do this. Okay? Our next example is going to cause a problem. So we're going to do our next example, and then we're going to come back to this one and talk about what we could do to shortcut the process, because we're going to have to shortcut it in the next one because our calculator will not let us do it. So let's come back to this problem in a second, but let's move on to number 3. 20 factorial. I'm not going to write it all down for the moment. I would like for you to take your calculator, and I'd like for your calculator to try to do 20 times 19 times 18 all the way down to the number 1. What happened?
Yeah, really short.
Okay, so it says 2 points. Most of yours probably say 2 point something. 2 point, tell me just a couple of digits.
2 point.
What? 2 point?
2.432.
We'll stop right there. There's more after that. Does it have an E at the end, a capital E? It has a capital E. And what's the number after the E? 18. Okay, does anybody know what it's doing? It's doing scientific notation. Okay, that capital E is shorthand notation. Your calculators all use it. Means times 10 to the 18th. That 18 afterwards means that that decimal point where you are right now wants you to move the decimal point 18 places to the right. This is a huge number, right? Why can't your calculator deal with it? Because it's got limited space across its screen. There's only so many places it can list out before it loses the ability to list them all, right? So that's not good, because it's doing something where it's abbreviating, because you've got all these decimals and it's not listing them all. So we need another way to be able to handle this to get an exact answer. And there is another way to handle that. Okay? I'm going to go back to the problem before and show you what it is, and then we'll use it because we have to on this next problem. Take a look at this numerator and this denominator. Do you see how they match up? These numbers at the end match these numbers right here perfectly, don't they? They do. And you learned somewhere in middle school, maybe the end of elementary, that there's the ability to cancel factors on the top and the bottom of fractions. These are just fractions with a bunch of multiplication. I can cancel them out. 4's cancel, 3's cancel, 2's cancel, 1's cancel. And I can do that because it's all multiplication. So what I'd like for you to try right now, real quick, is just multiply out 8, 7, 6, and 5. 1680. It's the same thing to God, isn't it? Yes, it is. It's the same thing. 1680. Not only that, but there's a shortcut on how you can write it too. Instead of writing out 4, 3, 2, 1, what's the shorthand notation that we learned on how to write down 4 times 3 times 2 times 1? Fact 4 with the exclamation mark. So if we get to a point where there's a 4 exclamation part on top and a 4 exclamation point on bottom, and they match exactly, not just they divide each other, but they have to match exactly, we have the ability to cancel out the 4 factorial on the top with the 4 factorial on the bottom. Now, that's all well and good, but we had another way to do this problem. Why does it matter? Well, it matters because I can't do the problem I'm on, number 3, the way I did number 2. It's too big. But what I can do is I can write out the 20 factorial like this. And instead of writing out 10 times 9 times 8, I can stop with 10 factorial. And why would I want to do that? Because there's a 10 factorial on bottom already. Now, it doesn't matter which one I rewrite, but I can rewrite one of the 10 factorials that's on the bottom as is. The other one, I need to write it out. Okay, so the 10 factorials that match perfectly exactly get to cancel. Try with your calculator again. 20 times 19 times 18 all the way down to 11, because that's what's my numerator now. Is it small enough? Can the calculator tolerate it? If it can, that's great, and we can stop and we can just do the problem right there. Renzi says no. Do you still get a scientific notation? Most calculators will still put it in scientific notation. Did yours do it as well, Samuel? Yeah, okay. So, yeah, it's still too big to do it that way. So now I need to figure out what to do. And I can't just do what I did before, right? Like, that doesn't match exactly, right? Over here, 4, 3, 2, 1 matched exactly. I don't have things matching exactly from top to bottom. But I still have factors that will cancel. Some of them cancel really nicely. For example, what is 4 times 3? It's 12. Do you have a 12 on top? Yep. 4 and 3 will cancel with the 12 on top. That's great. Do you see any others that you could pair up from the bottom to match with something on top? Nope, but you're getting closer.
2 times 10.
2 times 10 will work. The 2 and the 10 will pair up to cancel with the 20. Now, let me just say, the way in which you cancel it doesn't make any difference. So we're about to hit places along the way where you're like, oh, I thought I was going to cancel this, and she said I'm going to cancel that. That's okay. Cancel what you want to cancel. As long as they cancel, it doesn't matter. You're going to get the same answer. Okay, so I may not have any more places where they match perfectly right now, but do you see things that divide one another? How about the 9? What on top will divide by 9? 18. So instead of it canceling perfectly, I'm going to mark the 9 out with the 18, but the 18 is going to become a 2. That's okay. It still divides out. It got smaller. The goal is to get it smaller, right? Now, you can, and I will always, cancel everything in the denominator with something on top. That will always happen. If at some point you're like, I've canceled a lot of stuff, let's just see if it works again with my calculator, you can do that too. Okay, that's a possibility. At some point it will reduce small enough on top that you can divide by what's left on bottom. But we're going to cancel them all out because we can. How about the 8? What will the 8 cancel with? 8 and 16 will give me a 2. How about the 7? 7 and 14 will give me a 2. Let's skip over the 6 for the moment and let's go to the 5. What about my 5? 5 and 15. So I don't get a 2 on that one, right? I get a 3. Okay. There's not something exactly written that will cancel with the 6. But there is something else we could do. Any thoughts?
Multiply together on top and then try to divide it?
You could. You could flip what we're doing. Do you see a 2 and a 3 on top? What's 2 times 3? 6. So I could pair something on top up with this to cancel the bottom of 6. It's not the only way to do it, but it's an option. At that point, if you didn't want to cancel the 6, you could multiply everything out on top and then divide it by 6. That'd be fine too. Wouldn't hurt anything. Here's the deal. Some of you have very neat handwriting. Some of you do not. My handwriting is actually really neat. And I still lose track of the numbers if I'm not being really careful. And because I can't see the work that you've written down, I can't do partial credit very well for this. So you need to be really, really careful not to lose numbers. So let's check and see what we have. I will write them down on this one. I don't usually write them down. I'll do it a different way in a moment. But I have left a 19 and a 2, a 17 and a 2, a 13 and an 11. Those are the values that I have remaining at this point that I need to multiply together. What is the product of those numbers?
184,756.
And your calculator did it, didn't it? Yeah. If your calculator ever gives you scientific notation, you need to know there's more cancellation you could have done before you went to the calculator. Every problem will have an exact value, okay, that your calculator can tolerate. Okay, we're going to make things a little bit abstract. You'll see where this formula comes from in a little bit. It comes in section 10.3. All we're doing, however, with it at this point is simply starting with something that looks like a formula, and we're given the n and the r to put into the formula. So this n is 28. We'll go inside this for this n and this n. And this r is 15. We'll go inside here for the, whoops, try that again, for the r and the r. Okay, so we're just going to do a substitution. Make a mess of things. So the n is the 28 that goes on top. The r is the 15, right? So it goes on bottom here. And then I have 28 minus 15 inside the parentheses. And before I get started, I'm going to subtract. So it's 15 factorial. And then what's 28 minus 15? 13 factorial. Notice the denominator. I have a 15 and I have a 13. What's 15 plus 13? 28. It matches the top. That's not coincidental. That will happen in one of our formulas every single time. We'll mention it when we get there and talk more about that formula. But this is where we're starting. So at this point right now, the problem looks a lot like the problem we just did that had the 20 factorial on the top and the 10 factorial on bottom, right? So we're going to write our 28 all the way down until it matches one of the factorials on bottom. You can pick. You can stop at the 13 or you can stop at the 15. I usually stop the first opportunity I have to stop, which means I'm going to stop at 15. This one is really long to write out. It'll probably take me 2 lines. So we'll see. 28, 27, 26, 25, 24, 23, 22, 21, 20, 19, 18, 17, 16, and 15 factorial. The 15 factorial matches. I'll just write it where it was before at the beginning. But then I need to write out the 13. So 13, 12, 11, 10, 9, 8, 7, 6, 5. Hang on. What am I to do? 4, 3, 2, and 1. Okay. So I've written them all out. The 15s are going to cancel. And we can go down the line canceling, but I usually try to do pairing things up because it cancels things out quicker. So do you see any pairs of things that will cancel from the denominator that match to the numerator? 3 and 9 will make a 27. What else?
2 and 10.
Okay, the 10 and the 2 will make 20. 7 and 4 will make 28. I think that might be it for my pairs. I don't see any other pairs. Do you see any other pairs? Okay, let's just get on the list then now. 13. When I talk about my list, I'm talking about the denominator. I want the denominator to clear out. So what will the 13 in the denominator cancel with in the numerator?
26.
It's a 26. What's 26 divided by 13? 2. How about my 12? Okay, the 12 will cancel with the what did you say? 24, sorry, thank you. 24, there we go. That will leave me with a 2 as well. How about my 11? 11 will cancel with 22, leaving me with another 2. Okay, how about my 8? 8 will cancel with 16, leaving me with another 2. 6. 6 will actually work on this one. 6 and 18. 6 and 18, so the 18 will be a 3 now. And 5? 5 with a 25 will give me a 5. So I'm going to go back. We could list them out like I did the last time where I could list all the pieces that are remaining. I'm just going to circle them. So I have 2, 5, 2, 23, 2, 21, 19, 3, 17, I almost forgot it. The 2. Does yours look about as clean as mine? It's messy, right? It's really easy to lose one of these kids along the way. Don't lose the kids, okay? All right. The number's really big, but your calculator can still handle it. It's not so big that it can't deal with it. What do you get when you multiply out this list?
37,042,160.
Yep. So my first class, I think there was like 6 different answers. People left things out across the way. It's just so easy to lose one of the numbers. So just be careful. Okay? Be careful not to lose any of the digits. Okay, so all of that is sort of like the backdrop of the section. The section had a title that said Fundamental Principle of Counting, right? So all of it's going to hinge, not all of it's going to hinge, but a lot of it's going to have to do with these factorials that are coming into play, and we'll use them further into section 10.3 as well. So let's take a look at what the Fundamental Principle of Counting says. And once again, the language is harder than it actually is to work with. So let's write it down in general first. For a task consisting of k separate parts where the number of ways to do the ith part is n sub I, then the number of ways to perform the task is n1 times n2 times n3 ... times nk. Okay, so I'm going to give you, before we actually do the examples that are in the notes, give you some verbal examples of where you've seen this used before. And hopefully at least one of them will be like, yeah, that makes sense, okay? So the first place we're going to start is in your closet, okay? So let's assume for the moment that either everything in your closet matches or you do not care about matching, okay? All right, and we're going to talk about outerwear. So in your closet, you have shirts, you have pants, skirts, shorts, whatever, and then you have shoes, okay? Those are the objects we're going to talk about. If you were to go into your closet and you were to count the number of shirts, there'd be a number associated with that. Let's say it's 20, okay? 20 shirts in your closet. I don't even know if 20 shirts will fit in your closets on campus, but let's pretend. 20. Then you've got, pants, shorts, and so forth, and let's say there's 8 of those, right? And then you have your shoes, and let's say that there's 5 of those, okay? If you wanted to figure out how many different outfits you could put together, you would multiply the number of tops, 20, times the number of bottoms, 8, times the number of shoes, 5, and that would be the total number of outfits that you could create. You're with me? That's fundamental principle of counting. Take your favorite drink place, whether it's Sonic or Starbucks or H2O or the gas station, for goodness sakes. It doesn't even matter. All right? There's a certain number of base choices of, we'll go with soda for the moment. So I'm going to use the gas station as an example. Okay, the gas station has a certain number of soda displays, with coffee, tea, whatever. That's one choice. It's whatever the base soda is, if you're limited to choosing one soda. And then you have some sort of a flavor, something you put in on top of it, right? So there's, like at the gas station, you might have a place where you can add in the strawberry, the vanilla, cherry is usually an option. I don't know, there's usually peach. Yeah, so they've got these flavors you can add in. So Sonic's the one that I always think about because it was not, I mean, it's within the last 10 years, Sonic had an ad campaign talking about the number of ways you could create your own Sonic drink. They were doing this with it. It was fundamental principle of counting. You can do this at a sandwich place the same way. Okay, so you go to the sandwich place like Subway or something like that, and you've got a certain number of bread choices. You've got a certain number of meat choices, a certain number of cheese choices, and we're going to ignore the vegetables for now. If you're just talking about the base sandwich, if you multiply the number of breads times the number of meats times the number of cheeses, that's the base number of sandwich options you have. Okay, you with me? So fundamental principle of counting, it's very commonly used. What we're going to do first is we're going to go back to our friends, Abigail, Bailey, Nate, David, and Elias, and Macy, and we're going to figure out how many ways we could create the same committees and groupings that we did before, but we're going to do it with the fundamental principle of counting. And here's how it works. This one says we have a president and a treasurer, okay, just like problem number 1 back in section 10.1, and they have to be different genders, different sexes. So we have president, we have treasurer, and there's 2 options. So I usually put 2 placeholders. First one for president, second one for treasurer. Now, how many different presidents do we have options of? 6, because there's 6 people, and all of them could be president. However, once I pick my president, how many different options do I have for treasurer? 3. Why is it 3 and not, say, 5?
Because they cannot be the same gender.
Right. So once we pick the first person, let's say we picked that it was Abigail. That means that I can't use any of the girls for the treasurer position. I can only use the boys that remain, which is 3 boys, so I put the 3 next. What's 6 times 3?
18.
How many did we get before? 18.
That's a time saver.
That's a time saver. It is. And it's especially a time saver if we had more than 6 people, right? Yeah. Okay. So let's do the second one. President, secretary, and treasurer. I'm choosing 3 things. So I have 3 options that I'm going to fill in blanks for. This one tells me that the president and the treasurer have to be girls. So how many options are in the first spot for president? 3, because there's 3 girls. How many are in the last spot for treasurer? 2, because I can't use the same person twice, right? They've got 1 role, one and only 1 role. How many options do I have for secretary? Nope. 4. Okay, so why is it 4?
Because you have 2 spots filled.
Okay, I already have 2 spots filled.
Yeah.
Okay, so I already chose my president, I already chose my treasurer. There's 4 people left. And it didn't tell me who has to be in the middle. Like, it didn't say it has to be a boy, right? Or that has to be a different gender or anything like that. It doesn't say that. Anybody that's left could be in that middle spot. There was 4. What is 3 times 4 times 2?
24.
Is that what we got before? Yes, it is. Cool, right? Okay, there is a caveat to the next one. It doesn't work particularly perfectly with this description, but I feel like to just leave them out sort of makes it look like I'm cheating you out of telling you this always works. There's a caveat, so let me show it to you. All right, remember our committee of 2 people? And remember we had this issue where once I listed Abigail with all the people, I didn't list her again with all the people? Remember that? Okay. It's going to make things work a little bit differently on this. So let's take a look. We're still choosing 2 things. Agreed? How many people can fill my first committee spot? 6. How many people can fill my second committee spot? 5. What's going to happen if I multiply 6 times 5? I get 30. What's my answer supposed to be? 15. Why in the world am I getting 30 instead of 15?
You're accounting for duplicates.
We're counting duplicates. I duplicated everybody. When I listed 6 times 5, it means I listed Abigail Bailey and I listed Bailey Abigail. Those aren't different people groups, right, for a committee because they don't have roles assigned. So when I have a committee on this one, I would actually have to divide by 2, and the reason is that I'm going to remove double counts. Now, the reality is that this doesn't work very well with a fundamental principle of counting structure. There's this weird thing happening because I've got to remove the double counts. So this isn't a great way of doing this particular problem. We will have a better way in section 10.3 to do this problem. But we can make amends for it. We can get the 15 we were supposed to get. Okay. 4 more questions in this section, and they're all based on random guessing on tests. Don't do that. Don't random guess on tests. It's not going to go well, and you're about to see why. Okay, so let's say quiz might be a better description because these are short, but it says test. So it says we've got a 6-question true or false test, and we're trying to find the number of ways we could mark our answer key if we were totally random guessing, right? That's the idea. So if I have 6 questions, I'm going to have 6 blanks. And it's a true-false test. So how many choices do I have for every question? 2. So I'm going to do a 2 in each blank. Fundamental principle of counting. Going to multiply all my 2's together. How many different ways are there to mark my answer key? Multiplication, not addition. Two times 2 times 2 times 2. What's it going to give you? Bigger.
Bigger times 2.
Yeah.
60.
There's 64. If I multiply 2 times 2 times 2 times 2 times 2 times 2, I will get 64. So if I am random guessing, I have a 1 out of 64 chance of getting a 100 on that quiz. I also have a 1 out of 64 chance of getting a 0. I mean, it's balanced, right? So yeah, I'm not likely to do all that great if I'm random guessing because there's 64 different options of how that answer key could have been correctly written. Make sense? Now, if you are systematically answering, it might be helpful to turn it into a multiple choice test. But if you're random guessing, it's not going to be. 9, same 6-question test. But now I don't have 2 answer choices each time. It's not true, false. It's multiple choice. How many choices do I have for each of my answers? 5. So instead of 2's everywhere, I have 5's everywhere. And you might think, well, yeah, it's going to get a little bit bigger. What is 5 times 5 times 5 times 5 times 5 times 5?
15,625.
Did it get a little bit bigger? No, it got a lot bigger, didn't it? There are 15,625 different ways that answer key could have been created. You have a 1 out of 15,625 chance of randomly getting the right answers. That's not good, right? That's not good. Are you with me? Yeah. Okay, let's do one more kind of test. The test we're going to do next is matching, or you can think of it like a test bank. So we have 5 answers, or 5 questions on the next 2 instead of 6. There's 5 questions. And we're going to do a matching test where there are 5 answer choices. And every answer is used exactly once. So you've done this before, right? So you've got the test bank. There's 5 choices. Once you pick one, you mark through it, right? So the first time that you're choosing an answer, how many answer choices do you have? 5. But once you use it, you mark it out. So the next answer choice, you have 4 choices. The next question you have 3, and then 1. We've seen this number today. Saw it about 20 minutes ago. This is 120. This is another way that we see factorials, right? This is 5 times 4 times 3 times 2 times 1. There's a 1 out of 120 chance on this test of getting the correct answer key, right? By random guessing. But if you had a test like this, where you don't have 5 choices you're picking from, you have more than that. Okay? So you still have a 5-question test. You still have an answer bank, but the answer bank doesn't have 5 choices in it. It has 10. So the first time you make a selection, how many choices do you have? 10. Now you still mark it out in this structure. Have you had the test too where you can have an answer show up more than once? That's worse. That's terrible. Okay, this one they've got it. It's only going to show up one time, so we've marked it out. So how many fewer choices? How many choices do we have the next time? 9, and then 8, and 6. Okay. Now you might think, okay, well, I doubled the answer choices. This should double the number of choices ways that I can have to create my test.
30,000.
So not double, right? It went from 120 choices up to 30,000 choices. It's pretty easy to make the test harder, isn't it? Especially for students who are random guessing. You just add a few more answer choices in there, right? Increase the complexity just a little bit, and I actually have a lot more difficult way of guessing these. Now, we'll see why this happens later, but this is actually 10 factorial divided by 5 factorial, which we saw earlier on. We did it with 20s and 10s, but this is actually what this is. This is 10 factorial divided, I'm sorry, just 1 5 factorial on bottom. I take it back, just one. 10 factorial divided by 5 factorial. That's what this actually is. Okay? All right. That's it for 10-2.